Hello, my name is Markus Ohlenforst and I'm the Managing Director of IconPro. In this presentation I'm going to speak about predictive quality and process optimization in production based on machine learning. The motivation for this is how classical quality management is normally done nowadays. Classical quality management includes quality inspection on the one hand and statistical process control on the other hand. Based on that, you get the quality data of your parts during inspection, either for some samples that you draw from your production or for every part in production. And from this information, with the help of statistical process control tools like QDAS, for example, you get the insights about process capabilities or process instabilities regarding quality. This is done to detect if a certain process is getting unstable with regard to quality, or if there is a high number of low quality parts or scrap rates respectively. Question is, how is it possible to reduce the inspection efforts while controlling the process at the same time? And how to optimize the process to reduce scrap rates and improve quality based on the quality data that we have. The principle is called predictive quality, and this includes the consideration of quality data on the one hand and production data on the other. On the production data side, purchased part or material information is considered, as well as manufacturing parameters, environment conditions and assembly parameters. And on the quality data side, we have the quality data, for example, geometric inspection values of certain parts that have been measured. Goal is here to be able, or to get able, by the help of systematic correlations that are found in between production and quality data, to predict the quality that a certain part is going to have already during production, and then to reduce inspection efforts by only inspecting those parts which are predicted to be critical with regard to quality. On the other hand, scrap rates should be decreased or quality improved by optimizing process parameters on the production data side based on insights or correlations that were learned historically in between production data and quality data. What are the necessary preconditions to do something like this? What we see here are the cycles in production, so from the development cycle over the manufacturing or actual production cycle to the user cycle at the end, where a lot of data is produced and collected throughout this whole product life cycle, beginning with the development cycle side with data that is collected in FEM by FEM or CAD processes or databases, going further to the production cycle where MES databases, CAQ databases or SPC databases are filled with process data, machine data, quality data, up to the user cycle where there is data, for example, from customer relationship management tools. So we concentrate for predictive quality, of course, on the production cycle and the databases which reside in there. So first precondition is relevant data must be available, typically from ERP, MES or SPC databases, so electronic resource planning databases like SAP or Oracle. MES means manufacturing execution system databases monitoring the manufacturing process or processes in production, and SPC, so statistical process control databases containing the quality data. Traceability must be given, of course, so it must be able to refer which quality data belongs to which production data for certain individual parts. And of course, the data amount and quality must be given, which is necessary, and this should only be checked if the other preconditions are already met, but is at the end the sufficient condition. If this is fulfilled, then a predictive quality project makes sense, where it is in the first place about to search if there are any systematic relationships that can be found and then later on exploited to gain some benefit financial benefit from this. The first example I'm going to talk about is a predictive quality example coming from the turbocharger production. So here we did a project where we looked at different processes. So what we see here on the left are the machining processes in the turbocharger production. So machining processes for the production of the bearing and housing of the center wheel, the turbine wheel and shaft. Then comes a center section assembly consisting of different assembly sub-steps, here in total about 20 assembly sub-steps that are being done before the part then goes to the high-speed balancing, consisting here of an initial balancing and a final balancing process. So purchased parts were also assembled in addition to the parts that were machined before the assembly. Here the data was traceable, meaning it could be referred which data from the balancing process belongs to which data from the assembly process for certain parts. And the data was extracted from MES and SPC databases. The tasks or questions were here: is it possible to predict the outcome of the initial balancing process based on the assembly data before? First. Second, is it possible to predict the outcome of the final balancing process based on the initial balancing information? And then last but not least, is it possible to even predict the final balancing outcome based already on the assembly data? So first of all, the customers, before they approached us, of course, did also own analyses, and these results which they gained, we reproduced in the first place here. And these covered actually results from one-dimensional correlation analyses, which were done here for the three different tasks. So in between assembly and initial balancing, in between initial and final balancing, and in between assembly and final balancing. And what can be seen here is that the one-dimensional correlation coefficient values are pretty low, only higher if it comes to relationships in between one data set, so in between the data set for initial balancing, for example. But this doesn't help us because this only represents correlations in between different input parameters. We actually want to predict a certain output based on inputs. So this doesn't make sense, and this here confirms actually at the end that high-dimensional, high non-linear analysis, which is in best case data-driven and machine learning based, is needed. And this is what we have done, and this is here the results that we have gained for analysis number 2, so in between the initial and the final balancing data. So after heavy pre-processing, a nested neural network combination here proved to perform the best. And in summary, we had an accuracy of 87.3% regarding the tolerance prediction after final balancing, meaning here that in 87.3% of the cases we could predict if a certain part is going to be of tolerance class A, of tolerance class B, or not good after final balancing. This information can be used to potentially reduce the final balancing efforts by 20%, because then the parts which are bad at the end anyway can be just taken away and not be processed in the final balancing step. So here we've got a risk of 0.05% that something which is actually bad is still going to be declared as good. And when calculating the net cost benefit due to the reduced final balancing efforts, this has also been taken into consideration. But here at the end, the net cost benefit was estimated to be significant. Detailed results can here be seen on the right. So another subtask here was to actually show the feature importances, meaning how important is a certain input feature for the output, so for the tolerance class. What we see here are two bar plots showing feature importances of different input parameters. Here on the top left for the tolerance A result, meaning these parameters here have these input parameters here have these importances to reach a tolerance A result. On the bottom right, we see the importances of certain input features for a certain G value that should come out at the end, or for certain G values that should come out at the end for different rotational speeds. What we can also see here are different colors. So blue means that this is an input feature which would have to be increased to increase the probability for the wished result. So here for tolerance A, and red on the top left, and red would mean that this value would have to be decreased to reach the regarded, to reach a higher probability of the regarded results. These insights can directly be taken to take some actions into place for optimizing the outputs. So to perform some low-level process optimization. Of course, here relationships in between the different input characteristics or input features are not really considered, because it could happen that if you decrease the one, you would have to increase the other. This is also something our software can put out, but this would be too complex to be shown here, and you are open to ask any questions about that, of course. This would be it regarding the predictive quality use case example for the turbocharger production. Next, I will present you some activities that we have performed in a predictive quality project in the field of the shaver, electrical shaver production. Here it's about the plastic housings of these electrical shavers, which we can also see here, see here in this picture. So these plastic housings are produced in an injection molding process, and then afterwards certain characteristics of this plastic housing are measured geometrically on coordinate measurement machines in the course of quality inspection. And these characteristics include, for example, diameters of some boreholes or some holes in the plastic housing, as well as some distances. And the data, quality and injection molding data here was drawn from MES and SPC databases and was also traceable, meaning here that we could refer the quality data of a certain part to the production data or the injection molding data of a certain part. Task here was to search for systematic relationships in between production and quality data, of course, with the help of our software suite, and to check if it is possible to predict the numerical geometric inspection values based on the injection molding data already. Here we see a summary of the results for 6 different characteristics that are measured on the plastic housing parts on the CMM. And here it was shown that the random forest model included in our suite performed the best and gave the best results. Here the accuracy is measured with these R-square values, since we want to predict a certain numerical value. And a value of 1 here would mean that the predicted value is exactly the true value, and the closer here the values are to 1, the better it is, of course. What we can see right away is that for the first 3 characteristics here on the x-axis, the values on the y-axis, so the R-square values, are pretty high, while for the latter 3 they are lower. But in summary, these very good results here could be produced already after a first fast analysis. Here we see scatter plots for the true values versus the predicted values for the 3 first characteristics, and points on the diagonal would mean here that the true value is exactly the predicted value and would represent then an R-squared value of 1. What we can see here is that all the points are pretty close to the diagonal, and what you have to have in mind here is that all of these points are within the tolerance limit of the characteristics. So we are here able to predict the numerical value of a certain geometric characteristic within the actual tolerance limit very well, and from this you can actually derive that it is for sure possible to predict if a certain part is going to be not okay. So outside of the tolerance limit, since we already inside of the tolerance limit can predict the numerical value very well. In summary, the data contains strong systematic relationships for at least 3 to 4 different characteristics. Strong relationships here are due to only one significant process step before the geometrical measurement, which is the injection molding process, from which we have almost all the data from the MES system. And regarding the mentioned upper and lower tolerance limit shown in the scatter plots, predicting whether a part is going to be okay or not okay would be an easy task, as would be process optimization that can be built up in that with the help of our software. What is it actually that we are developing right now? So we are developing standard software for predictive quality and process optimization in close collaboration with QDAS, which is a company producing statistics software for production since more than 20 years and is highly established in this field. And the software is called ARES. QDAS IconPro ARES software, and offers the following features. So data can be fed from files or databases to the software. The data pre-processing, which actually represents one or even the most important part of the whole analysis, is done automatically by the software, so that the end user of the software doesn't have to do very much about this. This is something where we can say, from our experiences, is heavy manual work normally to get to the best results at the end by combining a multitude of pre-processing with a multitude of processing or modeling steps. So a simple data assessment can be done to judge or to evaluate the data quality and amount of the data. Automated machine learning modeling is of course included. There we include the most modern automated machine learning libraries that we extend even with further models by our own. Accuracies can be visualized as well as confidences, so we don't only give the accuracy, we also give how confident are we about the result with a probability of 95%. The input feature importances can be automatically plotted, as we have seen before. Models can then, after training, be saved and then be deployed for the integration and use in production. Change points, so points where the behavior of the process or the process chain suddenly changes, can be detected automatically. Online learning is not available yet, but will be made available, meaning that the software will continuously learn with every new sample that it actually sees, instead of training it from time to time with historical data and then using the trained model for further prediction for a certain time period, after which then the training is performed again. And at the end, we also derive policy and optimization models. This is already in development right now to be able to recommend certain process configurations instead of only giving the input importances and the recommendation if to decrease or increase. We actually at the end even give a recommendation, a multi-dimensional recommendation for the process parameter configuration, also considering interactions in between different input parameters. So if this is of interest for you and you ask yourself how would this look like if you would like to work with us, these are the steps which we see here. So it starts with the introduction, where we will take a closer look together with you at your processes or your process chain. We will take a look at the available data sources as well as at the already available historical data. Then we will, in case, perform a test study where we will first assess the data by judging or evaluating the data quality and amount, and then doing some test analyses to derive a feasibility. So to derive actually a recommendation for you, does it make sense to further pursue this use case or not? And only if the real project starts. So until there, actually everything is for free and can be done with us in a short amount of time. And then the implementation starts, the real implementation starts based on your processes, based on your data and data sources, where we will adapt our software suite to your needs and also validate the outputs of the software, of course, before we will then deploy it and install or derive recommendations in the case of that you don't want actually a software but rather service analysis. At the end, we will monitor the results or the outcome of the installation of the software respectively to make sure that the results are actually sustainable and stable, and that you you gain a certain benefit from that, which could be either the reduction of inspection efforts or even the reduction of scrap rates by either predicting the parts which are not okay and then only inspecting those ones, or by optimizing your process parameters by deriving the best process parameter configuration. So this would be it from my side for now. I would be happy if you would send us some feedback, or if you would be even interested in doing a project with us or installing our software. So thanks for your attention, thanks for listening. Maybe you can also take a look at our other videos, and hear you or see you soon. Goodbye.